Any quantum measurement is intrinsically statistical. We need to repeat several times the same experiment in order to have an idea of what the original quantum states looks like, or used to look. Here, we'll see how the quantum measurement works in a quantum computer, from a mathematical and practical point of view. And as always, let's do it with an example. Let's talk about the Heisenberg model. When considering a magnetic problem, we are usually concerned about the interaction between adjacent spin particles. This is a many-body problem that is hard to compute numerically. The Heisenberg Hamiltonian looks like this. There is a projection of the spin vectors, coupled by the exchange constant. The other half of the Hamiltonian considers the existence of an external magnetic field. We find the geomagnetic ratio, the Bohr-Magnetic constant, and the eventual external magnetic field. Classically, we will try to solve this problem using perturbation theory, or a mean field approach. But again, very hard to solve. Let's simplify our lives and start assuming some usual things. The external magnetic interaction seems a little hard, so let's consider none. Now, if we restrain ourselves to a nearest neighbor interaction, the exchange constant is the same for everyone, and the double sum becomes a simple one. I have changed the notation to the usual use of the Pauli matrices. Finally, if we consider that there are only two spin particles, and we explicit the Pauli matrices to the usual qubit gates, we get the final Heisenberg Hamiltonian. The new H coefficients are just some specific constants of our problem and technology, so they will not bother us, and we see that one single spin will be encoded into a qubit as usual. If we study a little bit this qubit Hamiltonian, we see that there is an important property between the Pauli chains. When calculating the commutators, we see that all Pauli chains are zero. Remember in our math courses, this means that there exists a vector base where we can simultaneously measure them. This is great, because that's not often the case. So, can we go and start our quantum measurement? Not so fast. The issue here is that there are some Y gates, and we cannot directly measure Y gates. X and Z projection are easy though. So, let's use this excuse to discuss a little about basis change. Knowing what basis change to do is not simple. There are current investigations that propose some isomorphisms that even help simplifying the Hamiltonians, but there is no straight answer. Here, I will just propose to you an heuristic transformation. Let's start with the first Pauli chain. If we consider the equivalent quantum circuit of two X gates, we have this. Now, let's use a mathematical equality that uses the C0, aka control not gates. We have then the circuit equivalence. Now, if we have the great idea to apply a C0 gate to the left and to the right of both circuits, we get these new circuits. I have used the fact that the usual quantum gates are Hermitian, so unitary. So in particular, my C0 gates are their own inverse. So when putting them side by side, they cancel each other out. Now, if we add some Hadamard gates at the extremities again, we have these circuits. Using the common relation between X and Z gates, we can simplify to this minimal circuit. Let's try out the same method with the Z gates. The double Z gate mathematical equivalent is now this one. As before, two C0 gates are applied to both ends. And because of unitarity, they cancel out. Now the Hadamard gates. They are also their inverse, so we can just erase them when side by side. This little circuit is our final proposal. At last, let's tackle the problematic Pauli chain. The double Y circuit is no surprise to you now. The relation that we will use this time is this one. The circuit becomes this. The complex I coefficient will be mathematically considered afterwards. For the moment, I will continue the method by applying the C0 gates to the left and to the right. And now, a little ruse. Let's take advantage of the unitarity property by applying two C0 gates between the Z and the X gates. Next step, the Hadamard gates. Same trick with Hadamard gates, between the introduced C0s. What do we get? Oh, the circuits founded for the double X circuit. And also the double Z circuit. So we can just use them. The equivalent circuit is now a simple double Z gate. What have we got so far? We have seen that transforming our Pauli chains as follows results in three simple circuits. And more importantly, these equivalent circuits can be easily measured using the Z projection axis. this was the basis transformation that we were looking for. If we call this part over here the operator U, then this part here will be the operator U dagger, because it is its emission. It can be confusing the fact that the quantum circuit is read from left to right, but the operator notation is read from right to left. Be aware. Mathematically, if we consider what will happen to our Hamiltonian if sandwiched between these two unitary operators, our new Hamiltonian will be this. And using the results we have just demonstrated, it simplifies to this new form that we graciously call a Hamiltonian. The minus sign comes from the double complex product that we omit in the double Y circuit demonstration. How to use this new Hamiltonian? Let's consider two qubits that we call Q0 and Q1. Also consider an ansatz, any ansatz. This ansatz is usually a well-chosen quantum circuit that will hopefully prepare the quantum system in a desired quantum state of interest. In variational problems, the quantum state of interest is the state that minimizes the cost function, or in chemical problems, the ground state wave function that minimizes the energy of the system. For our purpose, without any loss of generality, when the circuit is started, the state function is ket 0, 0, and after the ansatz is applied, the quantum state psi is a linear combination of all possible outcomes. Mathematically, it means that if we express the expected value of the Hamiltonian with this ket, it can be written like this. Where is the Hamiltonian? Easy, we can use our usual trick, with the transformation operator U and U dagger, making the Hamiltonian appear. And if we define psi prime as U dagger psi, we can write down that measuring the Hamiltonian with our ansatz is equivalent to measuring the Hamiltonian with our new defined ket. In order to get this new quantum state, it suffices to apply U dagger to the ansatz circuit. So this time, it starts with the ket 0, 0. After the ansatz, we have the ket psi, and after U dagger, we have the ket psi prime, now with its own complex coefficients. Calculating the expected value will be written as this. Now let's explicit these terms. The first term, when considering only the ket part, will be as shown. The operators identity and z are projected into the four possible outcomes. When the identity finds any state, a 0 or a 1, it does nothing to it, so we can just ignore it. But when the z-gate is applied to ket 1, it changes the sign. So for all the kets that have a 1 for qubit 0, there will be a change of sign. The entire bracket of this term will be this expression, with the models of the coefficients. We can do the same for the remaining brackets. We have now explicitly written down the expected value of the Hamiltonian. Now let's get to the main idea behind quantum measurement. It consists on getting those complex amplitudes. If we prepare the state C prime once, the state function will be as expected, the linear combination of all possible outcomes. But when projecting the state into our computational basis, it means when measuring the state of our qubits, the state will collapse to a certain well-defined state. For instance, the ket 1, 0, which means that after measurement, the qubit 0 is in the state 0, and the qubit 1 is in the state 1. If we do that again, we found out that both qubits are measured in state 1. The probability of measuring one outcome or another is exactly the modulus square of the complex coefficients. In other words, the probability of measuring both qubits at the 0 state approaches the limit of the ratio of 0, 0 when n, the total number of measurements, tends to infinity. Here card for cardinal, or number of times 0, 0 was measured. The same for the others. Of course, we won't do an infinite times the measurement. It depends on the precision we demand. Here, to color my example, we will do 10,000 measurements. Try to count with me. 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, Okay, let's just let the computer do its job. Good, it's finished. This is the final countdown I just invented to serve my example. This distribution really depends on the chosen ansatz and the tuning parameters. The ansatz choice and the parameters are not explained in this video. In my invented outcome, 3000 is the number of times 0, 0 appeared, and so the same for the others. This gives us the probability amplitude we needed to measure our Hamiltonian, or as it is equivalent, to measure the Hamiltonian expected value. And because the H coefficients are specific to the problem, we can just use them and finally have the final value. When using terms as measurement or expected value, it is important to specify what are we talking about. For instance, in quantum chemistry, When saying that we measure the electronic energy of the system, we refer to the expected value of the Hamiltonian projected to the ground state wave function. This is not to confuse with the thousands of quantum measurements needed to specify the state function, or the additional change of bases when all the Pauli chains do not commute. Optimizing the choice of bases and simultaneous measurement is a huge area of research. I hope this video helped you understand how quantum measurement is done in a quantum computer. And as always, don't forget to stay curious. See you next time.